This is lesson 12 for AP Calculus. Starts off with a do now. I want you to work on this in your team. So there's 7 problems. You're going to work together, and every single person on the team does have to post this to their own Google Classroom. You have 15 minutes to work on it. The submissions will close 30 minutes after the class begins. So make sure you work on this and get it posted before then. You will have to ask the sub to use your phone. So here are the 7 problems. Write these down, pause the video and write these down, then work on them and post them to Google Classroom and come back to the video. Okay, so you should have posted those 7 problems to your Google Classroom, and now we're going to start the notes for lesson 12. For calculus, it's limits at infinity. We're going to be talking about limits as our x's are approaching very, very large positive numbers or very, very large negative numbers, and examine what is happening to the function. We're going to look at it graphically. We're going to look at it numerically. So another way to think of this is what's happening if you look at the graph on the far, far left as x is approaching negative infinity. That's what look to the left means. So here I have a function. It's the reciprocal function, 1 over x. And if we look at a graph of that, we can see, as we are using values of x that are getting larger and larger negatively, this function is flattening out, getting very, very close to the x-axis. If instead of examining on the left, we examine on the far right, meaning we're going to look as x is approaching very, very large positive numbers, we have another branch. Whoops, didn't mean to do that. We have this other branch here that as we go farther and farther out this way, it is approaching the x-axis on the far right as well. Now that would be the limit as x is approaching infinity of this function 1 over x. There's certain limits that we just need to know, that we need to memorize, and we can go through this process, but we just need to memorize. And one of those is a reciprocal function, which means 1 divided by x raised to some power. And it doesn't matter what the power is, positive or negative. We're just looking as this reciprocal function, and we're looking to the far, far left and the far, far right, or we're talking about as we plug in values of x that are getting larger and larger and larger. As the denominator gets larger, this function approaches 0. The next one that we need to know are power functions. Power functions, instead of reciprocal functions, look very similar, just not with the reciprocal. It's x to the n. Now we have different cases of this. So first, let's look as x is approaching very large positive numbers. So we have a larger and larger and larger base, raised to some power. And this is n, meaning it's an integer, a positive integer. So we're constantly getting larger and larger and larger, meaning there is no limit to the value of this function as x gets larger and larger and larger. We're looking far to the right, and that function, if we look at the graph of that, is going to be increasing without bound. So we say that it has a limit of infinity, positive infinity. When we're going to look to the far, far left of that same function, we have 2 separate cases of that. Okay. The first case is this limit will equal infinity, positive infinity, so long as the exponent is even, which means when we have x to an even degree on the far left, over on this, when we look this way, it's always going to be going up. So that's why the limit is positive infinity. But if my n is odd, meaning I have to the 3rd or the 5th or the 7th power, then on the left, it's going down towards negative infinity. So its limit is negative infinity. This is the limit definition of horizontal asymptotes, which is different than what we did in Algebra 2. It's an actual limit definition, and it says this. A function has a horizontal asymptote. We're just going to use the letter L to stand for that constant, whatever it is. So a function has a horizontal asymptote if the limit as x approaches positive infinity equals that limit, or the limit as x approaches negative infinity of that function equals L. The non-mathematical way of just saying that is as my inputs become very, very large, either negative or positive, the outputs, or the values of y, will get closer and closer to some constant value L. Even though it may never actually equal L, meaning f of x might never equal L. It could. We can even cross the horizontal asymptotes many, many times, but it might not. It doesn't have to ever equal this L. We're going to be, from now on, because now that we are calculus students, we will not just examine the degrees of the numerator and degrees of the denominator. We will always use limits to explain our horizontal asymptotes. So here's one example. Use limits to find the horizontal asymptotes of this function 3x plus 1 divided by x plus 2. So we're not going to use any of our Algebra 2 rationale about the degrees of numerator and degrees of denominator. We're going to use limits. So I'm going to do the positive limits, and I'm going to say as x is getting larger and larger positively, what is happening? Well, we could break this up into the limit of the numerator and the limit of the denominator. Or what we can just do is say, that, look at that rational function, factor out an x from both of them. Now, the reason to do that is we could then simplify this limit and break it up into individual limits. So if we reduce this, because the x divided by x cancels, well, we'll end up with these limits. The limit as x approaches infinity of 3 plus the limit of this whole thing that you see here. But we've memorized these reciprocals are 0, which means we've got the limit as x approaches infinity of the constant 3 divided by the limit as x approaches infinity of the constant 1, which is just 3 over 1, which is 3. We could do the same process, but now using negative infinity. And again, over here, we'd find out that we'd have the exact same result, meaning we'd get 3. Therefore, whether we look to the left or the right, this function has a horizontal asymptote of y equals 3. Now remember, it's this y equals 3. It's not just the number 3. Don't just say, oh, it's 3. That's the horizontal asymptote. When you're going to use the words horizontal asymptote, we have to say y equals 3 because it's an equation of a line. The limit is 3. The horizontal asymptote is y equals 3. When it says use limits to find horizontal asymptotes, that just indicates use limit language. So we use the definition. We say limit as x approaches infinity of 1 over x, which we know is 0. And we could do the same thing with negative infinity. It has a limit of 0. Since both the right-hand limit and the left-hand limit both equal 0, the function has one horizontal asymptote, and that is y equals 0. For this next one, we have one polynomial divided by another polynomial. We write down the limit as x approaches positive infinity. Factor out an x from each of those, and then we would simplify. So as we simplify this, we end up with these limits. Remember, you're breaking it all up into separate limits, but this is going to be 0. And the limit of a constant is just the constant. It's going to be 1 minus 0, which is just 1. Well, we don't need to write divided by 1, so we're just going to write it like this. And then the limit as x approaches infinity of this, well, that doesn't have a limit. We say in infinite, so it has no horizontal asymptote. Meaning this function on the right-hand side, since this is positive x, grows upward without bound. If we did the same thing with negative infinity, we would have this, but then now we plug in a negative infinity into this, it's going to equal negative infinity, meaning on the left-hand side, as x is approaching very, very large negative numbers, the function is going downward. It has no horizontal asymptote on the left. So neither on the right or the left does it have an asymptote. And on the right, it's going up, and on the left, it's going down. And this is describing it using limit definitions. When we think about how we describe this in Algebra 2, we looked at the pattern, not a definition, the pattern of the numerator and denominator, the degrees of the numerator and denominator. And what we did is we said, let's look at the leading terms of the numerator and the denominator. Once we just looked at the leading terms. And the old rationale when we were in Algebra 2 was that if they were the same degree, if the numerator and denominator had the same degree, then the asymptote is simply the ratio A divided by B. When the denominator was larger degree than the numerator, then it always had a horizontal asymptote of y equals 0. When the numerator had a larger degree than the denominator, then we'd say there was no horizontal asymptote at all. So this was the rationale we gave in Algebra 2. You aren't to use this rationale in this course any longer. You must talk about it with limits. And when we examine this pattern and we look at our limit definition, we create a pattern and the limit rule whenever you have a rational function, a polynomial in the numerator and a polynomial in the denominator, we can use the limit definition. Now remember, what we did is we only looked at the leading terms. We looked at the ax to the n and the bx to the m. Well, we can factor out from this rational function the ratio a divided by b. And then all we're left with is x to the n divided by x to the m, which we can write in this fashion. And this becomes the way we can look at the asymptote or the limit definition of an asymptote of a rational function. And so you'll need to use this formula. You have four more do nows. I want you to do these in class, get them posted to Google Classroom, and when you're done with that, then use the rest of the period to work on your homework. So here's your do nows. Again, you must use limit rules to justify your answer. Okay?